To understand modern agricultural management, we first have to look at the engineering of the traditional model. For decades, the standard was strictly linear. A farm took a single, isolated crop, poured in inputs like water and chemical fertilizer, extracted the yield, and vented the waste. Official agricultural recommendations and management practices were developed exclusively for these individual plants. Agronomists treated each crop as a standalone silo, optimizing its immediate environment for maximum yield without considering its broader surroundings. But this linear model fails in practical application because it ignores the residual effects that a crop leaves behind in the soil and the local environment. When the management ignores what a plant takes out of the dirt and what biological matter it leaves behind, the immediate consequence is systemic inefficiency. The operator constantly has to purchase external resources to replace what the previous crop depleted. Optimizing a single seed in a vacuum creates a leaky, vulnerable system that actively bleeds potential profit. To solve this inefficiency, agricultural science developed a comprehensive framework known as the systems approach. Under this approach, agronomists shifted their focus to the physical land, treating the plot as the primary unit of management rather than the individual crop. The academic text defines this rule directly, noting that under the systems approach, the land is a unit and management practices should be developed for all crops that are to be grown on a given piece of land. By expanding the scope to the entire plot, the operational goals shift toward maximizing efficient resource utilization across multiple seasons, maintaining long-term production stability, and securing higher net returns. Managing the entire parcel of land as a holistic environment provides more stability than micromanaging individual seeds. To build this framework, we have to establish what exactly constitutes a system in an academic context. A system is a specific set of elements or components that are strictly interrelated and interacting among themselves. They cannot operate in isolation. When we apply this logic to agriculture, the foundational layer is the cropping system. This is the practice of managing multiple distinct crops sequentially on the exact same piece of land. The residual chemical footprint and biomass left behind by the first harvest modifies the soil environment, deliberately establishing the growing conditions for the subsequent crop. We see this interrelated behavior formally defined in the textbook literature, confirming that these interactions are the defining characteristic of the model. Rotating crops on a shared plot improves efficiency, but it still limits the operational loop entirely to vegetation. To build an optimized agricultural engine, the framework must expand beyond plant life to include external biological enterprises. The next structural evolution in agricultural management is the comprehensive farming system. A farming system elevates the model by taking multiple, completely distinct farm enterprises and weaving them into one unified network. The literature lists several specific components that can plug into this architecture. Alongside the base cropping system, an operator might integrate dairying, piggery, poultry, fisheries, or beekeeping. We can introduce these new, distinct enterprise nodes into our conceptual model, placing them in parallel on the canvas. The defining rule of this expanded network remains: these seemingly separate enterprises must be deliberately interrelated to function as a system. The integrated farming system transforms these separate enterprises into a single, cohesive biological factory. The central operational mechanic that allows this web to function is the waste-to-input loop. The principle is straightforward. The end products or biological wastes of one specific enterprise are captured and utilized as the primary cost-saving inputs for another. To demonstrate this, let's isolate the connection between the dairying operation and the cropping system. A dairy enterprise generates a high volume of biological waste products, specifically dung, urine, and organic refuse. In a standalone operation, this is a severe liability, but here, this raw waste is captured and systematically processed into concentrated farmyard manure. That manure then acts as a direct, powerful input for the cropping system, reducing the need to import expensive synthetic chemical fertilizers. By internalizing the supply chain, the farming system turns an ecological liability into a primary economic asset. For this architecture to operate as a true loop, the flow of resources must go both ways. The end products of the cropping system have to reverse direction and support the dairy enterprise. When the crops are harvested, the process yields a large volume of residual plant matter, primarily straw. This straw is channeled back into the dairy operation, acting as the essential fodder to feed the cattle. The connection then moves beyond physical matter, introducing a third layer of integration, the cycling of mechanical energy and labor. The cattle provide the physical draft power required to execute field operations and grow the crops, closing the operational circuit. The textbook confirms this three-way cycle, noting that the straw becomes fodder, the cattle execute field operations, and the enterprises remain highly interrelated. This deep integration yields a nearly self-sustaining engine. The farm fuels itself, minimizes its waste, and minimizes its reliance on external purchased inputs. Viewing the entire operational network reveals a dynamic system of interrelated nodes. The internal recycling drives the engine, while external consumption drops. A successful system is an appropriate combination of enterprises tailored to the specific means and land available. The primary incentive for a farmer to adopt this complex network is to increase overall profitability by reducing overhead costs. It manages to secure those profits while operating within two critical constraints: maintaining the local ecological health and protecting the region's socioeconomic balance. In a properly designed farming system, maximizing economic margins and maintaining ecological health are mutually dependent outcomes of the exact same loop. The success of the individual operator eventually impacts the wider environment and society. While the traditional linear farming often degrades the surrounding environment as it expands, the comprehensive systems approach scales harmoniously. The text provides evidence that this methodology is designed with macro-level objectives built in, ensuring local ecological and socioeconomic balances hold firm while attempting to meet national goals. Localized, highly efficient farming systems aggregate. Together, they secure broader national agricultural goals, including food security and large-scale resource conservation. True broad-scale efficiency relies on optimizing the entire land ecosystem rather than isolating a single crop for extraction. The future of sustainable, profitable agriculture requires abandoning linear reductionism and mastering the mechanics of interconnected systems.